Okay, so now that we've discussed some of the origins of additive manufacturing and 3D printing and the history and some of the current trends and the state of the industry in general terms, let's start to get a little bit more detailed into the processes themselves and, of course, to start off that discussion, let's look at the design process that is involved with the additive manufacturing process. Okay, so we're going to talk about how you integrate additive manufacturing into an engineering design process, where it fits, and what are the methods and stages of that design process. All right, so and by the way, we're going to be talking about things in still in a general sense in terms of this design process. There are specifics that will need to be followed in terms of a design process if you're using a specific additive manufacturing process, or if you're using specific CAD software, or even STL modeling software or slicer software. Okay, so we're still a little bit general, although I am trying to, kind of fine tune and detail the things that we can at this point. But basically, in terms of the process for designing and producing a 3D printed object, okay, we have a 5-step process. Okay, the first thing we need to do is we need to have a CAD-based 3D model. Okay, we need to have some kind of 3D model. This is the one of the fundamental things with 3D printing is that we need to have a 3D CAD model, a model in our computer, a 3D model. Then from there, we're going to convert that or translate that into an STL file. Okay, so we'll talk about what an STL file is, but basically we're going to take the CAD model, the 3D model, and we're going to convert it to an STL file. Then that STL file is going to be sliced into many, many, many thousands of layers. Okay, so we're going to slice that into a series of layers. And then we're going to take those sliced layers, and basically we're going to bring them into a additive manufacturing system, whatever that is, whether it's a plastic fused deposition modeler or powder bed fusion metal processing system. It doesn't matter. We're going to bring those sliced layers into the additive manufacturing system, and the additive manufacturing machine is going to reassemble those sliced layers layer by layer, starting with the bottom one, and it's going to print each one of those layers, and from the bottom layer all the way to the top layer, and then it's done. Okay, and then what a lot of people fail to acknowledge or to remember is that there is a 5th step after you print the part, whether it's plastic or metal. Okay, regardless of the actual additive manufacturing process, there is always going to be some form of post-processing, part finishing. All right, and in some cases, especially for metal parts, this can be a substantial portion of the design process in terms of time, in terms of labor. So we can't really just forget about that part, because it can definitely affect the cost of the part, affect the quality of the part, and it's something that we need to acknowledge. Okay, so here's our basic 5-step process. And after we're done with that fifth step, then we have our final product, our 3D printed part. Okay. So now let's kind of expand that a little bit. Okay. And talk about each one of these steps with a little bit more detail so that we can see a little bit better what's going on in here. So these are going to be our 7 stages in the additive manufacturing print process. Okay. Again, regardless of the process that you're using, whether it's powder based, whether it's resin based or liquid based, or whether it's going to be solid based like plastic and metal. All of those fit within this. All right. So this is a generalized process for additive manufacturing. So first up, we need to have a 3D model. Okay. Whether it's a CAD model, or whether it's something that we develop using a 3D CAD system, such as Inventor, SolidWorks, Fusion 360, Creo, Parametric, whatever it is. Or whether we're going to get that 3D data from some type of scanning process. Okay. It doesn't matter. We need a 3D model. Okay. The second step is that we're going to convert that 3D model into a special type of 3D model that is called an STL file. Okay. Now, converting it to an STL file is basically going to take that model and convert it into a 3D model that is composed of thousands and thousands, maybe millions of triangular surfaces. Okay. So, and we'll talk about what exactly is going on with an STL file, but that's what an STL conversion does. Third step is we may need STL file manipulation. Okay. Now this will involve verifying the STL file, editing, or even repairing the STL file. Now, typically speaking, when you're generating your 3D model in a CAD system like Fusion 360, Inventor, SolidWorks, blah, 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 any of those CAD models, they're not really going to need STL file verifying, editing, and repairing. All right. That software will create a model that then will be able to be translated or converted into an STL file without any problems. Really, the problems happen when you're scanning a 3-dimensional object, a physical object, when you're scanning that object and you're creating a CAD model from scanned data, from scanned 3-dimensional points. Okay. A lot of times with that process, there are errors in the scanning, and your file will need to be repaired. Your STL file will have problems with it and will need to be repaired. Fourth up is creating what's called the build file. All right. And the build file is that slicing process. Now the software that's used to do this is often called a slicer file. A lot of this can be done automatically. So there's software out there that kind of does all this behind the scenes, but there is also slicer software that does this separately. Okay. That is, one option. But basically the build file creation involves slicing the STL file into a series of thousands of layers that are then going to be reassembled physically in the machine, in the additive manufacturing machine or the 3D printing machine. Now, the fifth step I put in here is machine setup. Okay. So this is assuming, and in most cases, this is completely necessary, that you will need to prepare the machine for printing. So whether that means adding the filament to it, and making sure the filament is set up, heating the table, the build surface, whether it's heating the chamber that the 3D print is going to be built in, whether it's heating up the powder in one of the powder bed fusion systems. All of these additive manufacturing machines, all of these 3D printing machines will require machine setup in some form or fashion. And of course, each machine, depending on the process, is going to have a different machine setup, but this is really a necessary step. So after we set up the machine, we're ready to print, and that's where we send the sliced file, right? The slicer file, the output of that is then sent to the 3D printing or 3D printer, and then the additive manufacturing machine or the 3D printer will build the part layer by layer. Okay, so basically it's reassembling the layers from the slicer into a physical model. And then finally, as we discussed in the last slide, the 7th step in this process is the post-processing. Okay, whether that's cleaning up the part, which oftentimes is necessary, or finishing the part, which many times you might want to do. Not all the time you have to finish it, but many times you want to finish the part to make it look presentable, to have it have the surface finish that you want, any of the properties that you need it to have, especially in the case of metal parts. All right. So those are our generalized 7-step process for additive manufacturing. Okay. Regardless of the additive manufacturing process in specifically, or the CAD or CAM software that you're using, specifically. All right, so let's burrow in a little bit deeper into each one of these. So stage 1 is 3D modeling. All right, so a 3D model is a prerequisite in the additive manufacturing process, and we have different 3D model types. We have our ubiquitous CAD model, whether it's a surface or a solid model. Right, we can use either a solid model or a surface. It doesn't have to be a solid model. We can create the 3D model from 3D scan data. All right, from a point cloud. Cloud meaning a 3-dimensional shape. We still need a 3D model, by the way. We can't do anything with 2D models. This 3D scan can be done with photogrammetry, light-based scanning systems. It can also be done with a medical scan, either an MRI or a CT scan. Will prepare 3-dimensional models that can be then sent to a 3D printer. One of the prerequisites with 3D scan data is that the data, the point cloud itself, has to be in the positive octant. Okay, so you'll hear this over and over again with scan data, and sometimes with CAD, data, depending on what kind of CAD system you're using. But basically, the positive octant is the 3-dimensional space where X, Y, and Z coordinates are all positive. Okay, all positive. So, to put things in a positive octant, really all you'll need to do is take your 3D data, your 3D model, and typically, translate it into, the positive octant. So it's not a big deal, but it can be confusing and cause errors if you don't have your 3D model in the positive octant. The other thing is that the model has to be fully enclosed. That is to say, there can't be any openings in your CAD model. All right. Especially, solid models, you don't really have that problem, but surface models, you can create a surface model. And of course, 3D scan data, you can have errors in that. So, a 3D model that's not in the positive octant and that's not fully enclosed will generate errors, and those errors will need to be fixed in that STL file manipulation step. All right, so let's talk a little bit about scanners. So 3D scanners, right? There's 2 basic types of 3D scanners. There's contact scanners and non-contact scanners. Probably the ones that you're most familiar with, at least from maybe looking on the internet or seeing people use, is the non-contact scanners. Those are basically light. They're using light, laser light or visible light to reflect off the object, and then there's going to be some type of computer system that is going to read that reflective data. The non-contact type come in 2 categories. We have the active and passive 3D scanners. The active basically is like the system I'm showing here in the figure, where we have a laser source that's going to shine or put a beam of light. That beam of light is going to strike the object and reflect off of it. And then there's going to be some type of a system that's going to read that reflective light and do some calculations to determine where that surface is in three-dimensional space. And this is done for thousands and thousands of points as you're moving the object or the light source around the object. With the passive system, there is no separate light source. What you're using is just ambient light in the atmosphere, in your room. And all that reflective light is going to be used. Now there's basically three types of passive systems. We have the stereoscopic system that uses two cameras to look at the same object. And an analysis is done on the differences between the two images to determine the distance at each point in the image. Okay. Again, you need a computer to do this, but stereoscopic. Photometric is a system that uses a single camera, such as your smartphone camera, and it involves taking several images using under varying light conditions, and then those images are reconstructed using software to create a three-dimensional representation of the object. And then finally, we have the silhouette type system. This system outlines the object by taking a sequence of images against a well-contrasted background. So those are all passive scanners. A contact scanner is like the one seen here. This is called a CMM, or coordinate measurement machine, and you can see this gentleman is using there's a probe attached to this long arm. The arm is fixed on the table. Okay, so the arm cannot move, but the base of the arm can't move, but the arm is articulated. And it has a touch probe on the end. And basically you're going to move this touch probe and touch all the parts, all the different surfaces, nooks and crannies of a three-dimensional object. And because the arm is attached to the ground and it's articulated, the computer system knows exactly where that touch probe, that point, is in space. And so as you touch things, it's going to be able to reconstruct that 3D model. So obviously that's a contact system for doing that, as opposed to a non-contact system. All right. Now I'm going to show this video real quick, and actually I'm going to fast forward a little bit, because this is going to show you one of the non-contact systems. This is using a laser light that's being reflected off the object and recorded. So I'm going to fast forward it a little bit here. Alright, so you can see this is a very easy process. You're basically pointing at the object, and you can see the reconstructed shape up here. This is what you would see in the computer. Very simple, very quick. Okay, very simple, very quick, but realize that this does take some checking. The STL file, or excuse me, the 3D CAD model that you're creating here is not always a perfect file, and many times you'll have to go in there, inspect it, repair it, make some changes to it. So, even though this is quick, it's not necessarily foolproof. Another fun thing that you can do is using the passive 3D optical scanner. Okay, and there's a number of different apps that you can download for your smartphone, and I have a table here of the different apps. So I encourage you to try this on your own. These are in many cases these are free. They work for the Apple or Android systems. And basically what you do is you put your object that you want to scan on some type of table surface, and you take a series of photos moving around the object. So high and low, all the way around the object. And the software, the app, is going to reconstruct that three-dimensional object in the smartphone. It's going to recreate it and create a CAD model of it. Again, it's not foolproof. So, sometimes depending on the software, you have to take lots of pictures to get really finer detail here. But, I encourage you to give this a shot, to try this out. All right. Another way that we can get 3D CAD data, that's very useful for engineers is to, employ, or use the 3D engineering analysis model. So, many of the CAD modeling systems, Inventor, Fusion 360, SolidWorks, all those usual ones, do computer-aided engineering analysis, right? CAE. And this involves, maybe aerodynamics or maybe a stress analysis. Well, that will generate a color 3D model, and that color 3D model can then be printed so that you can really print a three-dimensional version of your engineering analysis. And this is a really interesting tool for engineers, because most of the time we're looking at these models on a computer, and trying to move them around and interpret them on a computer can be a little limiting. Obviously, you can't carry a computer around with you necessarily and show everybody else the model. And it, especially for non-technical users, it can be very beneficial to actually be able to hand a person the model and say, here's where we see the highest amount of stress, and here's where we see the lowest amount of stress, and what can we do about it? Okay, so 3D engineering analysis is a great tool for 3D printing. GIS model data, GIS data, can be incorporated and printed in a 3D printer, which can create these really awesome looking, finely detailed and colorful topographic prints. Okay, so that's done. I also mentioned the the CT or MRI scanning data. This is used in the medical field for making models, either as a tool for surgeons to kind of know where they're going to be going in their surgery, so that they can prepare better their strategy for the surgery before you actually open the person up, which is definitely beneficial. Or it can be used to prepare parts, right, that are going to be integrated in the person. Oftentimes these are titanium metal parts. You can see here a skull injury having a cranial implant. So we can 3D print the shape of the skull so that we can really get a perfect fit on this cranial insert. You can see the knee replacement surgery now benefit from an exact scan of the person's knee shape, and prosthetics too can benefit from this 3D medical data. All right. So moving on from stage one, we move into stage two, which is going to be our conversion to STL files. Okay, so STL, first of all, there's a lot of confusion about what STL means. STL can mean a lot of things. I think it's a little ambiguous what the term STL stands for. Some people think it stands for stereolithography, the ST from stereo and the L from lithography, or standard tessellation language, tessellation meaning triangular, or standard triangle language. All right. So I believe the official version of STL is standard tessellation language, but a lot of people use it with any of these, and basically it doesn't matter. As long as you understand that it approximates the surface of your 3D model with triangles. Okay. And on the bottom left, you can see an example of an STL file and how it's recreating the curve shape with these triangles. Okay. And it's an approximation. That's the most important thing to understand. It's an approximation. So we cannot actually print perfect curves, right? Because our STL file is not made up of curves. It's made up of many, many, many thousands of triangles. Now, for our purposes and you know, to our naked eye, we oftentimes cannot see those triangles. They're so minute that for all intents and purposes, the curve looks like a curve. And accordingly, the most triangles that you have in your model, the better the approximation of the curve is going to be. Of course, more triangles means larger files, but with the computer systems that we have now, file size is not really an issue, okay? Highly curved surfaces must use many more triangles, all right? So when you have a lot of curves in your model, you'll notice that your STL file, model file, is going to be larger than if you're printing a cube. All right, so let's get a little bit more into the details, the nitty-gritty of the STL file. So the STL file, the format of that file, removes all of the construction data, right? Remember that the STL file is a conversion or translation of your 3D CAD model, right? So that STL file, that conversion is going to strip out all of your construction data, all the modeling history that you have in that. It's going to take out all of the units, right? And just work with unitless numbers. And it's also going to strip out any colors that you might have applied to your 3D CAD model, any material properties. All of that is going to be stripped away. So all you're going to be left with is are the numbers, the coordinate geometry of that 3D CAD model. Okay. The STL file contains unordered triangle vertices and surface normals. Okay. So if we look at one of these STL triangles, right? We, of course, with a triangle, we need 3 points to define a triangle. 1, 2, 3. Okay. So every triangle in the STL file is going to have 3 points. The order of those points is going to determine the outward facing normal, what's called a normal. A normal is the mathematical term or geometric term for a vector that is going to be pointing out of an object, perpendicular to the surface. Okay. And the way that the computer calculates that normal is it uses basically the right hand rule. And we sweep, with the right hand rule. This is also done with, current flow, and in an electrical system. As we wrap our fingers, right? So you would take your right hand, and as we wrap our fingers going from 1, 2 to 3. So in this case, we're going to be wrapping our fingers counterclockwise. When we point our thumb, that's the direction of the outward facing normal. Okay. So a counterclockwise rotation, and our thumb points out. And so this triangle right here has an outward facing normal, as it's shown with the big arrow here. Okay. So that's what each triangle is going to need: 3 points and a normal. Okay. So if we look at figure one would be the CAD model, right? This CAD model, when it's translated into an STL file, would look like this, right? Because you can't have a four-sided triangle, right? So every four or more sided object is going to have to be broken down into a series of triangles. So, the CAD model in figure 1 is translated into an STL file in figure 2. Okay. Figure 3 basically shows a more complex model, and showing you, maybe not in the best resolution because of the figure size, but how many triangles, all the triangles that would be, placed or used to recreate the shape of that object. It can be in binary or ASCII format. Binary format means the file is just a bunch of zeros and ones. ASCII format means the file can actually be read by you. If you print it out, you can actually read it and see what the STL file is. Typically, the ASCII format files are larger than the binary format. If you don't need to read your STL file, which you don't, then there's no reason to use the ASCII format. Many times, most times the binary format is all you want to use because the file is going to be smaller. The format for the STL file looks like this. If we take a snapshot of course, this is the ASCII format, but, first of all, there's going to be, the word solid and then the name of the solid file, right? And then it's going to have facet normal, and it's going to have the normal X, Y, and Z, location, right? And that's going to be that, actually, it's going to be that vector right there. The outer loop, vector V1, V2, and V3. So V1X, V1Y, V1Z, right? The XYZ points right there. Vector 2, point 2 and point 3, X, Y, and Z. And then it's going to say end loop, end facet. And then at the very end of the file, it's going to have a file name. Okay. So each triangle then is going to have 7 lines of code. Again, this is the ASCII format, but each triangle is going to have 7 lines of code. So you can imagine if you have thousands of triangles in your object, and most objects have at least several thousand, even the simplest object, if it has curves in it, is going to have several thousand triangles. Then you have 7 lines times however many triangles. Okay. Now let's look a little bit more into the creation of the STL files. So as I said, if you have 4 sides to an object, it's going to be translated into 2 triangles. Okay. 5 sides would be composed of 3 triangles. Right. 8 sides is going to be 6 triangles, and you can see that right here. So this means that a computer software can represent it as an n-gon, that is a polygon of n sides, is represented as n minus 2 number of triangles, right? So let's try this out. If we have an 8-sided object, an octagon, an 8-gon, is represented by 8 minus 2, 6 triangles. So if we have a 12-sided object, which is called a dodecagon, a 12-sided object, a 12-gon is represented as 12 minus 2, 10 triangles. Okay. So we can, that's a very simple, translation, equation to use. Now let's look at a sample STL file. Okay. So this, we'll kind of break this down. So here we have, the 3D model is called, or the STL file is called MySolid, right? And we can see our 7 line little triangle segments here, facet normal, right? Facet normal, each one. So I would ask you, how many triangles are there? All right. So I'll pause right here and I'll let you try to think of how many triangles there are, and then we'll come back. Okay, so I hope you're able to answer the question of how many triangles are represented in this solid file, STL file. So we can figure out the number of triangles by first identifying one of these 7-line segments that is one triangle. Remember, it starts at facet and it ends with end facet. And so in that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 triangles represented in this MySolid STL file. Okay. How many faces are there? All right. Now, to determine how many faces there are, we need to look at the facet normals. Okay. And so doing that, we can see that we have a facet normal. Notice that the facet normal has, remember, this is X, Y, and Z. This is a vector, right? So we have the vector here, 0x, 0y, -1 in the z. So this is pointing in the negative z direction, right? So that's what this -1 says. It's pointing in the -z direction, all right? By the way, this is a unit normal, so it's never going to be larger than 1. All of these numbers are unitized or normalized, so they're never going to be larger than 1 in this case. Or excuse me, I should say the facets, the facet normal is based on a unit normal. The vertexes are going to have different numbers depending on the size of the model. All right. So we'll see, you see here that we have two normals facing in the negative z direction. We have two normals facing in the negative x direction. Two normals facing in the positive y direction. Again, two normals facing in the positive x direction. Two normals facing in the negative y direction. And then two normals facing in the positive z direction. So now, if you were to construct this, maybe sketch something out, remember that normals point out from the planar shapes of the triangles, the planar triangles. So if you sketch this out, right, and you make sure that the normals point in the appropriate directions for each one of these, you can figure out how many faces there are. All right, now I'll pause here, or you can pause here, and then we can show that there's 6 faces, right? So then the question is, what is this object, right? So if we have 12 triangles, 6 faces, and you don't really have to, but you could put together each vertex, each triangle from each vertex, what you're going to end up with is a cube. And this is the representation of that, okay? So I would encourage you to go back. You know, obviously that was kind of a speedy run through on that. But to go back, now that you know what each one of these is, maybe print out this slide so that then you can draw the surface normals on them and understand what each triangle and what each surface normal represents. All right, so this is going to conclude part 1 of this lecture. We'll pick up with part 2. We'll finish up with the STL files, and we'll move on to the remaining stages in the design process.